Hello, my name is Peter Szczepanski, and in this video we'll be going over assignment 19, also known as 1001, also known as the planet analysis assignment. So why don't we go ahead and run this 5. And then after that, we run the function and call main. This was by far the hardest assignment I've had to do in this course, and luckily I get 4 minutes to explain what's going on. Okay, so as you can see here, here's one of the outputs. So here's like a graph and like a legend. The distance between Earth versus Mercury, Venus, and Mars. Without any like noise or randomness, and it's the average of 1,000 days. So as you can see here, the green line representing Mars, the dashed line representing the average, and then so on and so forth for all the other planets. As you can see here, Mars gets the farthest, has like the highest angle for it, while Mercury stays really consistent and like the closest. And you can tell by like the averages that like Mercury is the closest. So as soon as we exit out of this, then we see with noise how it all looks like, and it doesn't change too much. However, Mercury is at 9.66 and Venus is at 11.1. So while Venus is a little closer, and according to this graph, Mercury is still like closer by a long shot on average. Okay, so as soon as we get out of this, it checks the different effects based on the level of S, as you can see here. And then it computes like the 8x8 matrix I was told to do, the average distance in Earth years of every planet with each other. As you can see here, it has zeros going across because at Neptune and Neptune, obviously it's going to stay at 0. And then it's symmetric, true. Well, which means that it, 288, 288. Then the closest planet to Earth on average over 1,000 years is Mercury, so this just goes to show you that. Okay, so now we'll go ahead and answer the questions. So this is between Earth and Mars is 732. So first I computed the distance between Earth and Mars using my distance function. And then in my program, I created both planet objects, Earth and Mars, and then I called the distance function Earth, Mars 732. Okay, and then I roughly get 6.52 cm units, and then cm stands for a million miles. Okay, so how does my position and distance function work, and what trick did I use? So as you can see here, I used the angle equals 2 pi times the date, self-year, divided by self.year's length. And then in that way, assuming it's a perfect circular orbit on a 2D plane, I converted all the angles into radians. And then I used math cosine to get the x-coordinate and math sine to get the y-coordinate. And then after that, I just used like the simple like Euclidean distance, which is the square root of x minus x squared plus y minus y squared. Then I implemented that in Python. Okay, so for the 1,000-day time series, average periodic pattern and noise, I wrote a helper function to loop from 0 to 999 days. Then on each day, I computed the distance from Earth, Mercury, and Venus, and Mars using the distance function. I then store these distances into 3 lists and put on like a MATLAB plot. And then looking at the time series, you can see like the patterns like I showed earlier. Then where S stands for the standard deviation, and then I did NP random normal 0 to S, and then I had different S's. When S is increased, the average ranking of the planets basically does not change, and then yeah. And then the reason it adds the noise has to mean 0 over 1,000, it ends up canceling out over 1,000 days. So then how I formed the 8x8 matrix was I ordered the planet names and then created an 8x8 matrix, ran like the same thing I did for the third problem. I computed the position of each day and then stored each pairs of the planets. And then after the simulation over 1,000 years, I essentially like got the average of it and then put into a table. All right, thank you.